We start with a new chapter, elasticity. First, we are going to discuss what is the meaning of the elastic property of matter. Uh, from our common experience or day-to-day experience, we know that when uh, a rubber cord or something like this, if this is a rubber cord, first we can take 2 points A and B on this cord. Distance of separation is D, and it is pulled on both sides, stretched or pulled. It increases in length. After it is pulled, the length increases. But in order to increase a steel wire, if this is a rubber and if the same thing is done for a steel wire, what happens? We have to apply a very large amount of force compared to the force that is needed to stretch this rubber cord. Now, what happens when the force is applied onto it? This increases in length. Suppose the stretched rubber band looks like this. The point A gets shifted to here, A dash. B also gets shifted to a point, name it as B dash. Now the distance between the two will not remain D. Now the distance will change. So the relative distances between those 2 points have increased because we have applied a stretching force. If we had applied a compressive force, the distance would have decreased. Now, when equal and opposite external forces acts on the body at different point masses, now you can take this A or B to be different point masses of the body. Now they undergo relative displacements. Relative displacements means A has been shifted. Suppose A would have been at this position and B should have been at this position. So B has shifted to B dash, A to A dash. That means there is a relative displacement. As a result, the body undergoes a change in its shape or size, or both. Undergoes a change in its shape or size, or both. Now, in this condition, a reaction force develops inside the body which opposes this change. That means if we are trying to stretch this rubber cord, the rubber cord will try to contract itself. That means an equal and opposite force is developing inside the body which is opposing the change of elongation. That means the change is here, we are trying to elongate the string. Now, if this change lies within a definite limit, then the body regains its original state. When? If the force is withdrawn. That means, I repeat, when the force is withdrawn, the body regains its original shape if we are applying this force within a particular limit. Now, this property which opposes the deformation is present in all materials. This means this elastic property or the property of opposition of its change in shape and size is present in all kinds of materials. This is known as the general property of matter, that means the property known as elasticity. General property which is known as elasticity. That means we have to first or the most important that to keep in mind is elastic limit. This point must be discussed at the end of the chapter, but I am stating it now because this point is a vital thing in this chapter. Now, elastic limit means, as I have stated in the last statement that I have told, that if the change lies within a definite limit, that limit is known as the elastic limit. Because if we cross this elastic limit, the body, when the force is withdrawn, will not return back to its original size or shape. That means a part of the deformation will be permanent in this elastic material. I repeat, when this elastic limit is crossed, that means if the elastic limit for this rubber band is 20 newtons, I apply a force of more than 20 newtons, that means 22, 25 newtons, 25 newtons. That means, and after applying the 25 newtons, if I withdraw that force, the rubber band will not return back to its original shape. It will increase in its length. There will be an increase in its length slightly. That means a permanent deformation will be set into this band. Now, the first thing that we have to learn is the definition of elasticity that you will get in the book, or I can tell you the property by virtue of which a body resists the deformation in shape or volume or both due to external forces acting on it, and regains its original shape and volume when these external forces are withdrawn, is called elasticity. Now, some important points, very important points. First thing is the presence of impurity. Now, what happens when impurities are present? Impurities are present. If impurities are present in a metal, the elastic property will change. In present, elastic property changes. Elastic property changes. That means if impurities are present, elastic property changes. That means elastic property can increase or decrease according to the properties of the impurities. If the impurity is of a harder material, the elastic property will increase. It is a softer material, the elastic property will decrease. Now, if a metal is deformed frequently, time and again you are deforming it, then its elasticity decreases. That means you can write that if a metal is deformed frequently, what happens? The elasticity, its elasticity decreases. That means we are time and again deforming the wire. That means if we take a wire and try to bend it continuously 1, 2, 3, 4, 5 times, 7 times, 8 times, the more you bend it, the elastic property decreases. Now, this can be done for, you can write an example for a thick copper wire. Thick copper wire. For a thick copper wire, if it is twisted 10 times, 15 times, it becomes hard and brittle. That means it is ready to crack. Now, the third point, or point number C, the elasticity of a metal changes with temperature. That means elasticity changes with temperature. That means here temperature is a vital characteristic to understand elasticity. Now, usually for a metal, I can say for a metal, elasticity decreases when temperature increases and vice versa. Elasticity decreases when temperature increases. That means when particular iron, the blacksmith hits the iron and beats it with a hammer to change its shape. Until and unless the iron is made into red hot, you cannot hit it with a hammer and change its shape. That means when the blacksmith hits, or HEATS hits the iron rod, it becomes red hot. That means its elasticity decreases. Then only you can hammer it to a different shape. So elasticity changes with temperature, but there is an exception to this rule. Exception to this rule means exception is invar, INVAR. INVAR. Now, this is a alloy whose elasticity does not change with any change in temperature. Again, if a metal is first heated and then cooled, it is softened. Its elasticity gradually decreases. I repeat, If a metal is first heated and then cooled, then the that is it is softened, its elasticity gradually decreases. Now, some useful definitions. The first one is rigid body. Now, rigid body is an ideal case, absolutely ideal case, that is not found in nature. We can say that it can withstand any amount of force, that means deforming force, the force or external force that is applied to a body to change its shape and size, either decrease it or increase it. That means it can withstand any amount of force and prevent deformation of any kind. Now, if we can tell it in a different way, that means there is no relative displacement between the different parts of the body, no relative displacements between the different parts of the body. That is, the body does not undergo any deformation. In actual practice, no substance is perfectly rigid. Very near example to this rigid body case is diamond. Very near. It is not an absolute rigid body, but if we can say anything in nature which is very near to being a rigid body, is diamond. And another you can say glass also. Glass is also a rigid body. They are very close approximations of perfectly rigid body. Now you will be a little bit confused about this example, glass. You can understand diamond is a very hard substance. It can qualify as a rigid body, but why glass? Now glass is a supercooled liquid. Glass is a supercooled liquid. Okay, so glass, as it is a supercooled liquid, so glass can only break. You cannot deform it. If you try to change its shape and size, only thing that can happen is it can break. It will not accept your external force to change its shape and size. And if you release the force, if we move the force away, the glass will not come back to its original shape. It will hold its position. This second type of material, perfectly elastic body. Mistake. Perfectly elastic body. The first one is a rigid body. That means it can withstand any amount of force, but this is a perfectly rigid, perfectly elastic body. Now you have to understand the concept of perfectly elastic body very, very carefully, because what do we understand by the word perfectly elastic? That means if we are applying a force, what we have learnt in the first part of the video, that when we are applying a force, the body gets deformed. After we remove the force, the body regains back its original shape and size, but within the elastic limit. If the elastic limit is crossed, then the body will not return back to its original shape and size. That definition holds for perfectly elastic body. Now, what is a perfectly elastic body? It can withstand force, or first point that we can say that within elastic limit. The first point is within elastic limit, the body regains its shape and size after external force is withdrawn. After external force is withdrawn, the body regains its shape and size. But most important point is within elastic limit. If limit crossed, the body will not return back to its original shape and size. Different materials have different elastic limits. Now, what do we mean by that? That means if we can tell it in this way, that every body is perfectly elastic within its elastic limit. That means if we take a very soft thing, that means the elastic limit, what is the elastic limit? I can take it to be 10 newtons. Another body, very hard body, whose elastic limit is 1000 newtons. That means within the range of 10 newtons, that means if the external force does not cross the 10 newton limit, this body is also perfectly elastic within 10 newtons. This body is a perfectly elastic body within 100 newtons. That means this term is not fixed. This term relates to the elastic limit. If the elastic limit is less, that means elastic limit is 10 newton. That means within this range from 0 to 10 newtons, the body will act as a perfectly elastic body. If the force needed to change its shape is 1000 newtons, that means the elastic limit is 1000 newtons. That means this body will act as a perfectly elastic body. That means the property, that is, the body regains its shape and size after the force is withdrawn. This property will be followed by the body up till 1000 newtons. After that, it will not. The third category is the perfectly plastic or inelastic body. That means this will be just the opposite of this, or we can say when the elastic limit has crossed. When we have crossed the elastic limit by applying a force of more than 10 newtons on this body, the body after 10 newtons, 11 newtons, 12 newtons, 13 newtons will not return back to its original shape and size. It will hold its deformed state. It will stay in that deformed state. That means every body after it has crossed its elastic limit will act as a perfectly inelastic body. Now if we can describe it starting from 0 newtons, applying a force of very less amount, that means the near example can be clay. The near example can be clay. Clay is a material which is very soft. When we apply a slight amount of force on it, the deformation stays, and even after the withdrawal of the force, the deformation stays. Now the fourth one, or partly elastic, that is the maximum amount of materials that we handle every day in our life are all partly elastic. That means if after the withdrawal of external forces, deformed body only partially regains its original shape and volume. I repeat, body only partially regains its original shape and volume, then it is called a partly elastic body. Practically all materials can be treated as partly elastic. All kinds of materials. That means partly elastic is practically feasible. Practically those materials that we handle in our daily life are all partly elastic materials. That means only the force, when the force is withdrawn, a slight amount of deformation always stays in it. Now if we are asked, after studying all this, if we are asked that rubber and steel, which one is more elastic, which one is more elastic, that means steel is more elastic because we need to change its shape and size by applying a large amount of force compared to that of rubber. The fifth most important term is strain, strain, strain. Now under the influence of external forces, when a body gets deformed, the different parts of the body suffer relative displacements, as I've already stated in the starting part of the video. Now as a result, the body undergoes a change in length. It can undergo a change in length, volume, or in shape. Now this deformation or change in the dimension is called strain. Now strain means actually the deformation. Now how to measure this? How to measure the deformation? That means strain generally relates to three aspects: length, volume, and shape. How much? Length, volume, and shape. These three aspects of an object. Strain is always represented as the ratio of two identical quantities and has no unit. That means for longitudinal strain, if you can explain it like this, longitudinal strain, that means a rod is being pulled in this fashion. That means we are trying to increase the length of the rod. We are trying to increase the length of the rod. Now if the original length is L and the increase in length is delta L, so what is longitudinal strain? We can write delta L by L. So longitudinal strain means delta L by L. Now volume strain. What do you mean by volume strain? If we take a cube and apply a force on all sides to increase its volume, the cube becomes larger. That means original volume was V. Now the volume is V plus delta V. This is the change in length. So volume strain will be delta V by original volume. That means original length by original length is longitudinal strain, and change in volume by original volume is volume strain. This is how we can measure deformation. Now it has got no unit. Strain has got no unit because this is volume, this is also volume. This is a kind of length, this is also length. So there is no unit for strain. Now the sixth most important term is stress. Stress, simply you can learn it like this: force by area. That means the physical quantity which has the same dimension as stress is pressure. Pressure we know already, we have studied it, that means force by area. Stress also is force by area. That means when a body gets deformed under the influence of external forces, a reaction force develops in the body because of the elasticity. This force tries to resist the external forces and helps to bring the body back to its original shape or the unstrained condition after the deforming forces are withdrawn. The reaction force acting per unit area. Okay, the reaction force acting per unit area on the cross section of the body is called stress. This force is not the external force, mind you. This is the reaction force. You can explicitly tell it like this. This is the reaction force, so the force developed within the material to stop the deformation by area is stress. So stress means reaction force by area. Already, also we know that reaction force and the applied force are equal and opposite. Their magnitudes are same. So we can write also applied force by area of cross section of body. So the dimension of stress. What is the dimension of stress? Similar to pressure, force means ml t minus 2, area means L square. So ml minus 1 t minus 2. This is the dimension of stress. So unit of stress, what will be the unit? Similar to that of pressure, that is Newton per meter square in SI system, dyne per centimeter square in CGS system. Now there are two types of stress. One is normal stress, another is a shearing stress. SHEARING, shearing stress. Now I'm trying to draw a simple diagram to make you understand the difference between the two. Now if we apply a force in a angular style, the reaction force or the stress developed will be also in the same line but in the opposite direction. The arrow sign will be in the opposite direction. So you can take this part to be the applied force, and this reaction force we can tell it or name it as stress. Now if this stress is divided into two components, so one component will be along the tangent and one component will be along the perpendicular. So this stress is divided into two components. One is a normal component, one is a tangential component. Now what does this normal component? This is the normal stress. This is the normal stress which acts in a direction perpendicular to the material configuration. Now this is the tangential force or tangential stress. This is known as the shearing stress. So this is the shearing stress, this is the normal stress. Point number 7 is breaking load. Now what do we mean by breaking load? When an external force exceeds the elastic limit, then a strained body cannot return to its original size or shape even after the deforming force is withdrawn. In such a case, the body gets permanently deformed. Now, if the amount of the external force is increased gradually, if the amount of the external force is increased gradually, then for a particular value of the applied force, the body breaks or snaps. This magnitude of force or load for which the body breaks or snaps is called the breaking load of the body. So the braking load applied per unit area of the surface of the body is called the braking stress. If you can try to explain it in this way, that if for this body the elastic limit was 50 newtons, now the external force applied on the body is more than 50 newtons. Now suppose external force applied on the body is 60 newtons. That means the body will cross its elastic limit. Permanent deformations will be set into the body. If after 60 newtons we try to increase this force 60, 70, 80 newtons, at a point of time we can see that the body is going to break or tear off. That force or that load is known as the braking load. Now Hooke's law, simply we can write stress proportional to strain, but this is within the elastic limit, or we can say stress by strain is a constant term. Stress by strain is a constant term. This constant is called the modulus of elasticity. This constant is known as the modulus of elasticity. Therefore, the stress developed per unit stress developed per unit strain is defined as the modulus of rigidity. Sorry, the modulus elasticity. Sorry, modulus of elasticity. Now, this modulus depends on the material of the body. The modulus elasticity changes with temperature in general. Usually, its value decreases with an increase in temperature. Very important points to remember. The modulus depends on the material of the body. The modulus changes with temperature, and its general condition, its value decreases with an increase in temperature. Now we start with the modulus of rigidity. The first one is named after Young, known as Young's modulus. Starting the definition for every modulus, we have to state one word or one phrase in common, that is within the elastic limit. Within the elastic limit, longitudinal stress divided by longitudinal strain is called Young's modulus. That means if we can write Young's modulus within elastic limit, within elastic limit, longitudinal stress by longitudinal stress, sorry, longitudinal strain, longitudinal stress by longitudinal strain is known as Young's modulus, denoted by the letter Y, capital Y. Now let us take an example for longitudinal expansion. If we take a wire hanging from a particular point, the length, original length is L. Now if we hang a weight, suppose of a weight of mass m, that means the weight acting downwards is mg. This rod or this wire will increase in length, suppose delta L. So original length was L and the increase in length is delta L. Now what is the longitudinal stress by longitudinal strain? So Y equal to, we have already learned that longitudinal stress means F by A. Now force here is the weight of the block by A means area of cross section A, by longitudinal strain means delta L by L. Now mg, what is A pi r square? That means this is a rod or this is a wire, steel wire. Basically steel wires or rods are round in shape or circular in shape, to be precise. Circular shape means the cross section is a circle. The area of that is pi r square. So delta L by L. So this is the value of Young's modulus for wire of cross section of radius r if a weight mg is hung from it. Mathematically we can write it like this: mg by pi r square into L by delta L. So mgl, original name, by pi r square into delta L. So unit of Young's modulus, unit of Young's modulus is Newton per meter square, because strain has got no unit, Newton per meter square, or we can write Pascal. The second modulus is bulk modulus. Now what do you mean by bulk modulus? This is a sphere. Now if a expansive force, sorry, compressive force is applied onto this ball from all sides, the ball will get deformed under the influence of external forces. When a body undergoes increase or decrease in its volume without any change in shape, that means sphere remains a sphere, then the strain of the body is called bulk or volume modulus. Now the expression for this will be bulk modulus equal to volume stress by volume strain. Now mathematically we can write volume stress is the pressure P applied onto the ball. Pressure means force by area, that is volume stress. Now volume strain, change in volume by original volume. The original volume was this one, this was the original volume, and the volume after being compressed is V minus delta V. That means delta V amount of volume has been compressed. So delta V by V. Now we can put a minus sign here, because the ball has been compressed by the application of external pressure. As with the application of external pressure, the volume has decreased, so we have applied a minus sign, or put a minus sign in this. So PV by delta V. This is known as bulk modulus and denoted by capital K. Denoted by capital K. Young's modulus denoted by Y, and bulk modulus denoted by capital K. The reciprocal of K, that means the value for 1 by K, it is known as compressibility. The third modulus is the modulus of rigidity. Now modulus of rigidity is denoted by N, that means shearing stress by shearing strain. Shearing stress by shearing strain. I have already discussed about shearing